Okay, let's maybe start as more people like. So I hope people on Zoom can hear. And the mic here seems to be working. Okay, great. So this is going to be a three-part series, where we are basically building towards this agenda, which is to prove Ryan Williams's very recent breakthrough. So this is probably like a month and a half old or something like that. It's going to appear in stock this year, and it's a really cool result, and surprisingly like not very complicated in the sense that it just builds using some very nice tools. So in the course of these 3 lectures, that's what I'm going to build up to. So the rough plan for these lectures in reverse chronological order is that I want to tell you about Ryan Williams's breakthrough, do the proof of maybe not this precise result, but I might maybe be willing to have one extra log t of n factor or something. Hopefully that's not something that people are going to be disappointed about. But if you are very careful the way Ryan is, you can actually get this precise thing, but it's just, it'll make it easier from the exposition's point of view. And this really builds on a recent result by Cook and Mertz. In fact, Buhrman had presented it, I think maybe last year or something, which was this problem called the tree evaluation problem. And Cook and Mertz came up with a surprisingly space-efficient algorithm for this problem. Okay, and in fact, anyway, when we see the lecture on the tree evaluation problem, which is next Wednesday, I will tell you more about the history and why this problem was so. I mean, people really cared about this problem, and it started off by assuming that they felt that the tree evaluation problem will require log squared n. That was the belief, and in fact, there was an explicit conjecture made saying that it probably requires log squared n space, and there were a series of results that kept shaving off, and now it's made it like almost log n space. This is right. Yeah. In fact, Steve Cook had a reward for this thing, and his son actually managed to get the money for it as well. So that's going to be the main focus of the next lecture. And basically, Ryan Williams's breakthrough, you can, if you zoom out like sufficiently, it basically is reducing the question of efficient space simulations to somehow phrasing the simulation as a tree evaluation problem. And once you phrase it that way, it's somehow readily, the techniques of Cook and Mertz, you could just apply here and you get a really efficient algorithm. I just broadly say that the naive implementation would have been log squared n, but you were able to get nearly a square root saving on the naive implementation. That's basically what is happening here.
What was nodding his head like anything?
Dark too. Nodding his head, he was disappointed that he missed it or something. Okay. Good. So that's going to be the main focus of the next lecture. And today's lecture, though it's not particularly required for understanding Cook and Mertz's result. I mean, I could have just presented Cook and Mertz's result, but I think it is it's very good in terms of internalizing how the proofs, etc. work by looking at this concept called catalytic computation that was defined a few years ago. Okay, it's just a fun model, and there are lots of very nice questions. And in fact, I think after Cook and Mertz's result and Ryan's result and so on, there's actually been a lot of very recent results on catalytic computation as well. But today I just want to introduce the problem, tell you about catalytic computation, show some surprising things that you can do in catalytic computation, and we will leave it at that. In the next lecture, we will start with the tree evaluation problem. So just to make sure that we are all on the same page, I mean, this is, there are people who are joining for the first time, but this is lecture 15 of this complexity course. So there's some sort of background that has been developed so far. But just that the only thing that I would assume that you have some familiarity with are these classes L, NL, and co-NL, and P. Okay? And in fact, the last lecture, what we had seen was that NL equals co-NL. This is the Buhrman-Chelevshiny theorem. And we know that all of these classes are subclasses of P. Okay? And another thing that we saw a while back was Savage's theorem. where L squared is just, I'm just using shorthand to say that, it is DSPACE of log squared L. Okay, and this is Savage's theorem. And this is what we had seen so far. And if you think about it from the perspective of the machine model, like what is the machine doing? We are talking about Turing machines where there is a read-only input tape. And there's a bunch of work tapes that it has, which it can use. And I'm only going to charge the Turing machine for the work tapes that it uses. So any cell on the work tape that the Turing machine ever visits, I will think of it as like a part of its charge, and we're going to count the total number of cells that it visits. And because the input is read-only, you can't do any shenanigans like basically use the input for most of your work tape, etc. And the input is not counted in this. So this allows us to talk about sublinear space and stuff. So when you're talking about something like space log(n), you don't want to say that input itself is written, so that's like n space. So that's just to make sure that we are all on the same page. Okay, so what is catalytic computation? So let me try to briefly describe what catalytic computation is. In fact, I'll try to do it in the way that it does in the paper. So let's imagine that you want to solve a certain problem. And this is a problem that maybe requires, I don't know, maybe like a machine to solve. Except that your laptop is currently completely full. Okay, you have a 2 terabyte hard disk, but the 2 terabyte hard disk is completely filled with legally downloaded ISO images. And okay, so the point is you don't need it right away. You don't need those images right away. But it's like you don't want to lose them either. Okay, but you have roughly about 10 MB of free space that you have in this laptop. And now the question is, you have 10 MB of usable space, and you have 2 terabytes of some data that is written on it already. But I can use it if I want, but I need to somehow ensure that, like at the end of my computation, that 2 terabytes comes back to whatever it used to be, in whatever form it used to be. Okay, so this is going to be the requirement. And we are going to basically ask, can you do something more? Okay, can you do something non-trivial with this? So let me formalize what this is. So we are going to assume that there is a certain input X that is written there. We are once again going to assume that this is a read-only input tape. Okay, and there is this work tape as usual. Okay, and the difference here is that we are going to have something that we will call, sometimes it's referred to as the catalytic tape, and sometimes it's referred to as the auxiliary tape or something. But this auxiliary tape comes with something written on it. Let me just refer to as tau. I don't have any control on what is written on the auxiliary tape when I'm starting the computation. Okay, and now what you want to do is you want to do the computation, and the restriction is that at the end, the catalytic tape contents must be restored. Okay, so the catalytic tape starts off with some arbitrary content which you have no control over. You want your algorithm to work irrespective of what was written on the catalytic tape to begin with. And the requirement from these machines are that at the end of your computation, you do whatever you want to do with the catalytic tape. But when you finish your computation, the contents of the catalytic tape must be the tau that you started on. Okay, so such a thing is called catalytic computation. And in fact, we will refer to this space as the catalytic tape space. We will call it maybe C of n. This is the amount of catalytic tape contents you're using when you're solving some input instance of length n. And the work tape contents, I will use W of n or S of n, whichever you are more familiar with, sort of a thing. And we're going to define this class, which is C space of W of n comma C of n, which basically means like, what are problems that you can solve using such catalytic machines when it is provided a catalytic tape of length about C of n, and your work tape contents are about W. There's no requirement on what happens on the work tape contents. At the end of it, they could have some junk values in it, etc. That I don't care. But the catalytic tape content must return. And the reason this is called catalytic computation is because the inspiration is probably from chemistry or something, where there are experiments where you add a catalyst and then stuff happens, but at the end of the experiment, you somehow get the catalyst back. So it's like it seems to be useful initially to somehow start off something, but at the end of it, it's not like you consumed it in something. You got the thing back. Okay, so this is what catalytic space is. And I mean, the general convention, rather than dealing with two different W of n and C of n, we normally assume, and if there is a single parameter, we will just assume that the catalytic tape contents is like exponential in the work tape content. Okay, in some sense, I want my work tape to be able to at least index which cell of the catalytic tape I'm reading. Okay, that's the rough intuition for why this is the case. So most of the time, I'll actually drop this explicitly writing down what your catalytic tape contents are. In fact, throughout this lecture, we will be dealing with W of n being order log n. So the catalytic tape contents is like polynomial in it. Okay, that's the setup that we are going to have. Okay, now we're going to, the whole lecture is going to be like, what can we do with these special classes? So here's the first observation, which is catalytic log space certainly contains log space, which is basically you just don't touch the hard disk at all. Okay, I am supposed to return it to its original form. Let me not use it at all. I am allowed log space of workspace. I will just work with the workspace. And what we would really like to know is like, the main question is, is the containment strict? Like, are there things that catalytic log space is able to do, which on the face of it feels like I can't do with just log space? And the punchline here is going to be yes, obviously with an asterisk, because all of these are conditional results. I mean, like we don't even know if like L and P are different and stuff like that. So basically what we will exhibit is like, there are problems that at the moment we don't believe can be done in log space, but we will show that catalytic log space can actually do these problems. Okay, and throughout this lecture, I'm not going to deal with non-determinism at all. I'm not going to mention things like catalytic non-deterministic log space and stuff, although those are legitimate models as well. But we are going to just deal with catalytic log space, and we're going to ask, what can it do? That's going to be the crux of today's lecture. Okay, great. So the whole point of catalytic log space, etc., is that it somehow feels like whatever computation you need to do using those catalytic registers, or whatever that tape, you need to do something that is reversible repeating. Because the expectation seems to be that you start off with some arbitrary contents on it, which I have no control over. And somehow at the end of this computation, I'm supposed to return to those kinds of right? So what we want to do is I'm going to assume that this is just to abstract out and sort of see what sort of things are we allowed to do. And we're going to assume that what we have is a bunch of registers. Okay, let me just call this R1, R2, blah, 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 till Rm, where each of these Ris, the value it takes, okay, they all come from, I don't know, some ring R, but I would suggest you think of them as just integers for now. Like, don't worry about how large these integers are, etc. Maybe when it really comes to it, we will work with maybe the ring of integers modulo some number, so that each register is like it's like 1 byte of information or something like that, and you have many such bytes of information. And I'm working with a ring because I want to add and multiply stuff. Okay, I'm assuming that there is some notion of adding stuff and multiplying stuff. Okay, and you should think of a situation where each Ri is very small. Like the registers themselves are quite small, but I just have many of them. So for example, if I want to copy one register and keep it with me, like I can afford to do that using my work tape. Okay, it's just that I can't store all the register contents. That's too much to store. Okay, and what we're going to do is we're going to build something called reversible computation, which is going to be a sequence of instructions, which we're going to construct these instructions such that it's clearly reversible. Like whatever instruction you can do, I want a way to undo the instruction. Okay, so let me just tell you exactly what the instructions look like. So I want every instruction to be of the following form. You take a register Ri.
Sorry, I have a question.
Tell me.
So should we think of like the auxiliary thing to be broken up into M?
When I mean by the what, think of the catalytic tape as
okay.
small registers.
Yes.
And that's the model that we're going to have. And every instruction in this program that I'm going to build will look like the following form, which is Ri is going to be replaced by Ri plus minus Ui Uj, where each of these Uis could either be a constant or an input, that is one of the Xi's, like, whether it's this thing, or it could be another register. Okay, in fact, let me write J for this. When I mean another register, is that I'm not allowed to say Ri equals Ri plus Ri. I mean, technically that is still reversible, but the problem becomes if I make it Ri equals Ri minus Ri, then in some sense I've lost the value of what that Ri is. But if I replace Ri equals Ri plus Rj Rk, where J and K are two different registers, then obviously it's a reversible computation, because if you ask me to undo it, I will just replace the plus with a minus. Okay, so all our programs are going to be built with a sequence of instructions of this type. You can probably add a few more instructions. Like, for example, you could scale a register with maybe a non-zero. If you're working with rational numbers or something, maybe you can scale it with a non-zero rational number. Maybe you can multiply with a -1, or maybe you swap two registers. You can come up with your own thing, but hopefully this is already a rich enough class to work with. Okay, so let's take an example of a program. Like this could be one such program. It's a sequence of 4 instructions, where the first instruction looks like, you replace register 1 with R1 plus X. Then replace register 2 with register 2 plus R1 times R3, whatever the values were, and so on. Okay, this is an example of a reversible program. Okay, and if I asked you to compute the inverse, if I asked you to undo this program, what would you do? You'll basically have to start from the bottom, okay, and undo this thing. Undoing this is the same thing as replace R2 with R2 minus R1Z. And then you do whatever. So the reverse will sort of look like this. You just write the instructions in the other order, and you do the natural reversing thing. Okay, is this okay so far? So let's imagine that X, Y, Z, etc. are parts of the input. So they are all there in the input tape. So my instruction could be like, if the input bit was 1, then I'm going to replace R1 with R1 plus 1. That's what this roughly means. Okay, great. A special form of computation is what we will refer to as transparent computation. Eventually, at the end, this is a program, but I want this program to compute a function I care about. Like maybe I have a particular function f of x in mind. Now, what does it mean to say this program computes that function? Okay, so I'm going to say this is one example of computation, which is I will say this program transparently computes the function f of x, let's say on register R1, the first register or something, to mean whatever you start off with as the original values, after you run the program, the first register gets incremented by f of x. Registers 2 through n could have changed to some other values, depending on, because the whole thing probably needs to be reversible. So maybe there are some changes that happen there. But the only thing I'm expecting is irrespective of what the starting values were. If the starting values were tau1 through tau n, at the end of it, I want to ensure that register 1's value, which is tau1 prime, that value is tau1 plus f of x. I don't care at the moment about register 2 to register m's values. Okay, so previously we came up with what is our program model, like what sort of programs are you dealing with, and now we are saying if your program has to do something useful for me, which is that I have a particular function, I want you to compute the function. This is how I am expecting you to compute the function. Okay, just translate one of the register values by f of x using a reversible program. Is the definition okay so far? Okay, and a very specific form of transparent computation is what is referred to as clean computation, which is actually register 2 through register m's values stay whatever it used to be. Okay, at the end of it, register 1 value got translated by f of x, everything else stayed the same. So this in particular is a transparent computation, but it's an even stronger requirement from such a program. Okay. Now, just to get familiar with it, here is a simple claim that you can prove. Suppose someone gave you a transparent program, someone gave you a reversible program that transparently computes a function f of x. And in the process, you use some m registers and you computed it on some register. I don't care what it is. Okay. I claim if you are allowed to add one more register, if you're allowed to work with one more register, you can actually make this computation a clean computation, like without too much effort. So the size of the new program is going to be related to the old size. By the way, by size, I just mean how many instructions did you use? Okay, how many steps does this program take? And it's going to be related to this old program. Okay, do you have any thoughts?
Same town prime.
Good. So basically what we are going to do is I want to think of this as register, let's say tau 0, and then all the way till tau m. Tau 1 through tau m was what my old program was using. And tau 0 is this extra register that I have. And what I'm going to do is I first do R0. Maybe I replace this with R0 minus R1. That's the first instruction I do. Okay, so tau 0's value has now become tau 0 minus tau 1. I now run the program P. Okay, and then I'm going to do R0 replaced by R0 plus R1. And then I run the program P inverse. Sorry?
You're running P1 tau 1 up to tau.
Yeah. I run the program P. So P only knows of registers tau 1 through tau n. And at the end of it, maybe it's translating tau 1's value by f. Okay. And I want to claim this is actually a program that cleanly computes my function f. So let's just get a sense of it. Let's say to begin with, my value was tau 0. So after I execute this instruction, okay, let me put it as tau 0, tau 1 through tau m is what I started off with. After the first instruction, this has become tau 0 minus tau 1. Then I run the program P. At the end of that whole thing, this will become this plus f. But maybe tau 2 prime, etc. This will all become tau 2 prime through tau m prime. Okay. Now the next instruction was if R0 is being replaced by R0 plus whatever the value of R1 is. Okay. So that value now becomes this plus f. And now if you just sort of run the inverse of the program, all of these are going to get replaced with whatever their original values were. Okay. So this
One that looks like the left 4 instructions, it looks like commutator.
Yeah, like there are commutators everywhere. Like all of this is just going to be commutators one after another. Yeah. In fact, we'll see whenever please stuff. Okay. So, and what is the length of this new program? If the old program had some L instructions, this program has 2L plus 2 instructions. So the size of this is like, twice the size of P plus 2, maybe. Okay, all good so far? Great. So now, okay, I've told you what catalytic computation is. I've told you what transparent programs are. So transparently computing something, cleanly computing something. But we wanted to solve a certain problem, which is we wanted to understand what can catalytic Loff space do. How do we intend to use these transparent programs or transparent computation? So the way this is going to work is the following. So there is this input X. I mean, this actually is a question that Prerna also asked. So the input X is written, and there is this whatever catalytic tape that we have, and this is the work tape that we are dealing with. So I'm going to pretend the catalytic tape is broken up into several registers, each of which holding some ring element value to begin with. Okay. Now, what's the work tape used for? The work tape could be used for storing some register value. Like for instance, maybe you store the value of the first register on your work tape, run your catalytic computation. Now the first step value got translated, but you knew the old value. So you can use that to say, okay, then I know what f of x value is. And I can always put that value back into that place. So this is something that you would want to do. So roughly the work tape will be used to store that. And it might also be used to store some program related information. Like for example, I need to know which instruction should I execute right now. Okay, so maybe there is some program counter, etc. Basically, some way of you should know that which instruction you are executing so that you can do them in some sequence. Obviously, you're not going to write down the whole program on the work tape. You just need some mechanism to say that if someone told you execute the 42nd instruction, you should know what the 42nd instruction is. So 42 is what will probably be written on the work tape. So that you keep incrementing this counter and you figure out which instruction to execute and use it. So all of the programs that we are seeing today it'll be, for people who know, it'll be very uniform. So these considerations don't apply, but I'm just telling you that this is roughly what is going to be stored on the work tapes. No. The length of the program could be polynomially large. It could depend on the input length n. The finite state counter is some fixed finite number. So I can't store all of them within that. So I might have to store it elsewhere. Okay. So what we are going to now start doing is to get a sense of what can we compute catalytically, or transparently in the process. Now let's first get a sense of what are the objects we are trying to compute. Okay. We are trying to compute things of the form f of x1 through xn, where x takes value zeros or 1. But we are technically speaking, you should think of them as numbers, like things that correspond to elements in the ring R. Okay. And f is going to return something in the ring R. Okay. So this is just something from, I want to just write this as R to the n to R, whatever your ring R is. Okay. So naturally, this feels like the right sort of model to work with are like, things that are very algebraic in nature. Like, you want to take things like, suppose you can do f and g, can you do f plus g? If you could do f and g, can you do f times g? Like the natural model for understanding your notion of easiness for a certain function f might be in terms of something to do with algebraic stuff, maybe formulas, circuits, etc. And we're going to slowly go up this ladder. Okay. So basically the first thing that we want to do is to somehow show that if f is efficiently computable as a formula, I want to be able to say that you can transparently compute it. So to start with, let's do the simplest thing. Suppose you knew that f can be computed using some transparent program, or transparently computed using a program. I might keep switching these two. And suppose you knew that g can also be done using a program. Now there's a very easy program to basically compute f plus g. Okay. So I am using a subscript r to basically mean what is the register on which you are computing. Like when you're transparently computing something, that register is going to get translated by f. So obviously, if I translate by f and then translate by g, that's effectively translating by f plus g. Okay. So this is proof is okay. So obviously, the interesting thing is what happens, like how do you compute fg? Suppose you knew how to compute f and you knew how to compute g. How do you compute fg? Okay, in fact, throughout this thing, the trick will be in the computation of the product. Okay, because I hope you understand why this feels a little tricky, because the thing is the register started off with some value. Okay, so and it just got translated tau1 plus f and tau1 plus g. But from that, somehow I need to get rid of that extra cross terms and so on and get whatever. Okay, so this was actually done in, I think, Richard Cleve's thesis. Okay, so I'll tell you how you do it, and it's hard to sort of motivate what is going on. So I'm going to define this new instruction. Let me call it sigma. It's a one instruction thing. And what this does is it does R1 minus R2, R3. That's what this instruction sigma is. It replaces R1. Sorry, I should have written. It replaces R1 with this. This is clearly a like one instruction program. Now here is this program that's going to be. So I first run the program for F, but with respect to register 2. Okay. Then I'm going to run this sigma. And then I run the program for G with respect to register 3. You can imagine if you had a program that was doing it on register 1, swap 1 and 3, do whatever, etc. Okay. And now you do sigma inverse. And now I'm going to run the program for F, but the reverse of the program. Run sigma again. And then I'm going to run the program for G. Again, the reverse of the program. And then run sigma inverse. And I claim at the end of this will do precisely what you want it to do. It feels like a miraculous thing, but we will just see that in the proof. Let's just track the values. So initially it's tau1, tau2, and tau3. Okay. After I execute the first instruction, okay, this is going to become this plus F. Okay. Then I execute the instruction sigma. What is that going to become? This is going to become this minus tau2, tau3 minus F tau3. That is after we ran this instruction. Now we run this. So that's going to become this plus G. Okay. And now I apply sigma inverse, which is like replacing the first register with the sum of the product of these two. I mean, that plus these two. So that is, what is that going to be? That's going to be tau2, tau3 plus tau2G plus F tau3 plus FG. Okay, so far, how far have we gone? We've gone till here. The next one is I need to do the inverse of this. That's as good as you remove the F part of it. Okay, and once again, I need to subtract off these two. So that is going to be what? Minus tau2, tau3 minus tau2G. And then finally, I do G inverse, which means this G goes away. And then now I add tau2, tau3. And hopefully everything cancels off. F tau3, and there is a plus F tau3. There is a plus tau2G, there is a minus tau2G. There is a tau2, tau3, there is a tau2, tau3. So the only thing that remains at the end is tau1 plus FG. And tau2 and tau3 have returned to what their old values. Okay. And okay. So if you knew that F was something you can do using L1 instructions, and G was something you can do using L2 instructions, roughly speaking, this looks like twice L1 plus L2 plus some chiller. Okay, there's some few extra steps that you have done. Okay, is this okay so far? So this basically you can put together and you basically get this result of Benor and Cleve that says that suppose someone told you that F was computable by a formula which looks like a fan-in-2 formula. Like everything looks like pluses and multiplications. Okay, and it has depth D. Okay, and if you just run the program, like do a plus, if it is a plus gate, you do the obvious thing. If it is a product gate, you do the obvious thing. And you just work out what is the final length of the program that will turn out to be. You will actually get that this is a program of length about 4 power n. Okay, I hope this is something that you can sort of see that, every time one lower depth, it's like you need to do this, you need to double the size and it will become roughly, it will basically lead to some quadratic growth. Okay, you will eventually end up with 4 power d. And the cool thing about Benor and Cleve is that the number of registers it used is just 3 registers. Okay, in R1, R2, and R3, it just does the whole game. Okay, is this okay? I mean, are there any questions about this? It's a really cool result. And in fact, for people who have, for example, seen, who were there in the algebraic complexity course or something, saying that this depth I wanted to be small is actually without loss of generality. If someone gave you a small formula, turns out there is always a way to depth reduce it and ensure that the depth is only logarithmic in the size of the formula. Okay, this is a very classic result of Brent and Spira. So it basically will tell you that if you think of d as like log s, 4 power d is like s squared. So it tells you that if you have a formula of size s, Benor and Cleve tells you how to construct a transparent program using the 3 registers of length poly in S. Okay, is this clear? So you don't need to know that this thing is, but it at least tells you that you now suddenly you can do a large class of things. Okay.
Sigma changes 3 registers, but
No, sigma only changes 1 register. R1's value is going to get replaced.
to compute and then we don't know how many registers were used to.
So I'm assuming, so for you do the whole thing via induction. So we assume that if f was just a variable, certainly 3 registers are enough. Because I can just increment one of the registers by the corresponding variable. So at the base case, 3 were enough. You just keep doing it again and again, and you basically tells you that as long as you have 1 free register, like f is going to use, let's say, register 2, g is going to use register 3, then I can put f plus g in register, sorry, fg in register 1. So you can always keep cycling between the 3 of them. It's a really, really cool proof. Maybe a little magical. This also, hopefully, it looks like a commutator. Maybe it's like a commutator of commutators or something. There's some, clearly there is a commutator version. By the way, I keep using the word commutator. I don't know how many people know this. Commutator is this thing that shows up in so many contexts. It's basically, it's things of the form do A, do B, undo A, undo B. Like you undo things in the wrong order. That's what a commutator is. And surprisingly, it's like very powerful in many contexts. Okay. So what we have seen so far is this result of Benor and Cleve, which, I've just stated that result in the context of transparent computation or clean computation or whatever.
Question?
Yes.
So Benor and Cleve does not use this particular model. Its model is much weaker.
So this is like Benor and Cleve expressed in this way. So the model of Benor and Cleve, actually, the way they want to compute a function f is they want to replace a register R1 with R1 plus f times R2. So it's a slightly different model, but I just stated Benor and Cleve's thing in this context. In fact, this is actually more like the Cleve's thesis interpretation of Benor and Cleve. By the way, finding Cleve's thesis was actually a surprisingly hard task. I couldn't find this online. I eventually ended up asking Abhibav in Waterloo, and he managed to go to the library there, get an electronic version. No, he didn't even get it from the library. He actually wrote to Cleve. Yeah, he wrote to Cleve and then got his thesis. And this is the version that's there in Richard Cleve's thesis. Yeah, did that answer your question?
A way to show that you can still show the theorem as a corollary, despite the fact that it's a much weaker model.
So here, when sorry, which corollary do you mean?
No, can you actually show Benor and Cleve is a corollary of what the more general theorem that you proved?
So, okay, so the original statement of Benor and Cleve. Yeah, okay. Actually, I don't have a very clear way of doing it, but somehow in the original statement of Benor and Cleve, the commutator they work with is rather simple. There is no interleaving of sigma that shows up there. It's usually something that looks like you run the program for f, run the program for g, undo f, undo g. Somehow that works. And but I don't have here is a simple way of going from the statement we have proved to Cleve's original. Benor and Cleve's original statement.
Let me restate. I think Benor and Cleve will eventually give you a branching program. I don't think the present model gives you a branching.
Okay, good. So yes, this is not a skew program. Okay, that's true. That's true. Yeah. Yeah, but it gives a branching program here. Branching programs usually you can't multiply 2 registers. Here I'm doing Yeah, I'm doing something more general. Banner and Cleve actually had a stronger statement where they had much weaker programs and they showed something similar. Okay, great. So now to go one step higher, for people who have seen algebraic complexity and so on, right now we have done formulas. So the next two things that's going to happen is I'm going to go from formulas to branching programs, and I'm going to go from branching programs to circuits. That's going to be what we do in the rest, as much as possible, this thing. So we're going to start with this observation that the construction above that we did, like even if this ring R was non-commutative, I want to claim the same construction works. In fact, this was the reason why I was particularly careful to make sure that I was writing things like F times tau3 and tau2 times G. I mean, I could have just said that, F tau3 and G tau2, etc. But I explicitly wrote it in this. I kept the order of the multiplication the same, just to show that, even if you assume that F tau3 could be different from tau3F, this, whatever the argument that we had here, continues to work. Okay, it's a small observation, but we're going to use this observation to sort of say that we can do something more than just formulas. Okay, let me maybe give some high-level picture of where we are going. I eventually want to show that NL is in catalytic log space. The canonical problem in NL is you're given a directed graph. I want to figure out, is there a path from S to T? And we are going to go there. And somehow this problem is more like a branching program-ish thing. And that's where we'll see the whole thing. Okay. So the simple observation at this point is that the plus and the multiplication gadget that we had above, it would have worked even if the things in R didn't come. Okay. So therefore, I'm going to ask the more general version of this question, which is, rather than the registers being a single number or something, suppose the registers were now matrices. Like each register is like a matrix of some, it's a K cross K matrix. Okay. I'm thinking of it as a K cross K matrix. And suppose I want to look at the product of all of these K cross K matrices. And maybe the 1/1th entry of this K cross K matrix is the polynomial, whatever, is the function I care about. Like my function, I have a bunch of K cross K matrices such that I can somehow embed this function in some entry of this product matrix. Okay, and what I want to know is, can I apply Banner and Cleve's trick in this setting? At the end of the day, this looks like M1 times M2 times M3 all the way till MS, which is like a small formula that is applied now on matrices. So I just want to know, can I just do the same argument now? I'm okay using more registers. Previously, we had only 3 registers. Maybe now I use more registers, and can I somehow make the whole thing work? Okay, so the way we are going to do this is I'm going to think of, the registers as now R1, R2, and R3. These are all what I will write as matrix registers. But this is really just our mental model. The matrix is made up of K-squared entries. So think of this big, whatever, this red register as really made up of K-squared usual registers. Okay, so each one, I want to think of it as K-squared usual registers. Okay, but I want to pretend to run the same algorithm that we had previously. Okay, like for instance, suppose I had an instruction that said, I want to replace R1 with R1 minus R2 times R3. This could be an instruction in this matrix program. But this is just, it's like a, I don't know, we've abstracted out and so on. I want to replace them with instructions on the base registers. Hopefully you can see that, each such instruction is just going to be a sequence of instructions in the base program. Right? Because if you have if this was a K cross K matrix times this, if I now ask you, what is the new 1,1th entry? The new 1,1th entry is going to be the old 1,1th entry minus this inner product or something. And the inner product looks like a sequence of K such instruction. You do y11 times whatever z11, y12 times z21, or sorry, whatever, something. I mean, like, you write the right inner product, etc. So an instruction in the red world will roughly translate to something that looks like, I don't know, k-squared instructions in this new world. Is it k-squared, k-cube, something? So k-squared times k. So it's like k-cube instructions. So this translates to k-cube instructions in the base world. So basically, you could have done the same thing. At the end of it, this basically says the function you care about showed up in the 1,1th entry. That's the same thing as going to be in the R1 register. There was one base register that corresponded to the 1,1th entry. That would have now gotten translated by F. So you could have done exactly whatever we did for Benor and Cleve. If you are now allowed to use something like 3 times k-squared registers, okay, you could just run the same thing for this new matrix product test. You just now end up using more registers than you used. Okay. So a corollary is that if you want to say that your function can be expressed as a product of matrices, where each entry looks like either a constant or one of the inputs, etc. And the 1,1th entry is a function you care about. Suppose you manage to do something of this nature. Then you can actually cleanly compute this function using a program of about length s squared times k cube or something. Because s squared in the matrix world, but each such instruction is like k cube instructions. So overall, you end up getting s squared times k cube. And you end up using something like order k squared registers. Okay, great. Okay, so now comes hopefully to the first concrete thing to sort of say that I want to say catalytic log space can do something that you don't believe can be done in just log space. And one problem here is the NL complete problem, which is the directed path. You're given a graph G, it's a directed graph, and there are 2 specific vertices S and T. And you just want to check, is there a directed path from S to T? Okay. And I only have logarithmic amount of workspace. And I want to show that this can actually be done in catalytic log space. You promise me that there is a polynomially large hard disk with values. I will repurpose that to actually get it, but ensure that at the end of it, the values stay the same. Okay, so do people have thoughts on how to proceed with this? I want to somehow reduce this to some bunch of matrices multiplied together. So the setup is that you are given a graph G and 2 specific vertices S and T. Okay. Good. So you have the adjacency matrix A. Now, what do I need to? I need to figure out is there a path from S to T at all? Good. I can do A power n, but unfortunately, the one stupid thing is that A power n will tell you if there is a path of length exactly n. Okay. So you could do this nonsense of just add self loops on all the vertices and then look at A power n. Okay. Now it's going to do some counting of how many paths for some suitable notion of paths that you have from vertex S to vertex T. I mean, maybe the number is not the same because there'll be some weird differences. But the point is, if I look at the S, Tth entry of this matrix, if this number was non-zero, then I know for a fact that there must be a path from S to T. And I know that if there was a path, there will be a path of length at most n. So A power n would have definitely captured it. Okay. So now the problem boils down to, I have this matrix. I need to figure out, is the S, Tth entry of this matrix 0 or non-zero? I need to compute the S, Tth entry. Now, we just did this. So suppose you have access to some matrix, some sequence of matrices, M1 through Mn. In this case, all the matrices turn out to be this A. And if the function you care about shows up at a particular entry, which in our case is showing up at the entry S, T, then it tells you how to compute that function catalytically. So we will use the work tape. We will imagine the work tape is made up of as many registers as you need. For this, I think we need something like, this is an n cross n matrix. There's a sequence of n matrices. So you probably need something like n power 4 registers or something, right? That's what you need for this. And so just run the old, there is just one small catch. Can someone see what the thing is? Whenever we
need 3 n squares.
oh, sorry, 3,
Order n squared.
yeah, order n squared. Order n squared is, okay, that's not the important part. The thing is, what is the ring you're going to work with?
You don't know very large numbers.
Yeah, so the point is, if I look at entries of a power n, it could potentially be n bits long. So if I want to work with some z mod n, such z mod some mz, it looks like that m has to be very large. It has to be like n bits long. And it like, I can't even copy the value of one register now. Because each register is like potentially holding n bits, and my work tape is not large enough to store those n bits. So, okay. So the question, what ring do work with? By the way, this is the same issue that would have shown up if someone gave you an integer matrix and asked you to compute the determinant. The naive way of doing it, numbers might explode. But there is usually a trick that you do to fix the situation.
Can we take modulus of prime?
Excellent. So all we are going to do, what we eventually care about is this entry non-zero? So we're going to basically do Chinese remainder theorem. Okay, so the fix, okay, try primes P1, P2, all the way till, let's say, the nth prime.
So this a power n, when you are multiplying two interests, you could replace the multiplication with the and addition with the or.
You could, then I need to somehow go back to the Benor and Cleve thing and somehow convince myself that that replacement is also a function I can do efficiently. Maybe there is a way to do that as well.
Then you need not worry about this.
Then I don't need to worry about this, but it's just that then somehow the model doesn't seem algebraic. It looks like
it's not a ring, right? You'll get a semi-ring where you can't invert things and it will be a problem. I mean, and you can't invert or you can't invert.
Oh yeah, I can't. Those are not invert. Maybe there's a way of fixing it, but anyway, so maybe there's a way of fixing it, but I think this will definitely work. So notice that the nth prime is not very large. Okay, the nth prime is certainly smaller than n squared. Because within some m numbers, there are m by log m primes. So there'll be nth prime is just n squared. So if you now ask me, is the s comma tth entry 0 mod 3 or not? Then all the registers are only going to be in 0 mod 3. So each register is over a very small ring. So what I will do is, on my work tape, I will just try one prime at a time. And I will do this for the first n primes. And if that entry was 0 mod pi for all of these pi's, then I know for a fact that the entry must have been 0 to begin. And if any of the primes give me a non-zero value, I immediately know, oh, it must have been non-zero to begin with. So I have a... Yeah, so I'm going to try number 1. I will check if it is prime doing brute force, because this number is so small, I can actually afford to try every number less than it and see if it divides. Okay, keep trying the next one. I'll just make sure that I'm trying at least primes until n squared. And once each of the catalytic computations, I'll probably have to do something like.
And in this case, without doing additional work, the brute force checking is almost forced on us, right? Because we have to do this in the work tape.
Yeah, we have to do this in the work tape.
So,
yeah.
Which is log space.
So
first, we are checking our potentially log n bits.
Oh yes.
So in a clever primality test, I mean, we'll have to talk about space complexity of it.
Yeah, but usually the space complexity of the trivial algorithm is small.
Yeah, exactly.
Yeah, but yes.
Because,
yes, that's right. That's right. Yeah. Okay, so that basically will eventually say that, okay, check this for tri primes. If any pi shows whatever the nth, whatever the s comma tth entry is not equal to 0 mod pi. Okay, return whatever. Yes, after undoing. I mean, because you're also supposed to undo the whole I mean, just make sure that whatever you have done on the work tape, like undo, copy your final answer, and then if the catalytic tape is slightly changed, just put things back. Okay, so just do that. So basically, this now tells you that NL is a subset of CL. Okay, are there any questions so far?
Right, no, just restating the issue that the problem was we knew how to do A to the N as a clean computation, but the primitive operations here were going to be
Ring operations.
Ring operations. But the point is the numbers here could blow up. So we don't know how to do those.
So the thing is, you could have potentially chosen your ring to be Z mod MZ, where M is larger than any of the entries that could potentially show up. So then you know that non-zero means non-zero, like non-zero over integer.
N factorial could possibly show up in A to the N. Maybe there
are
all possible.
Yes, maybe every single path is
which is N bits.
Yeah.
But the workspace is.
So because eventually, if you tell me that I have to copy the register 1's value to begin with, I mean, register 1 would have had to be as large as, to accommodate these numbers, which means that I can't even copy register 1's original value to begin with. I can't keep track of that. But on the other hand, if you work modulo small primes, then each register is a tiny register which you can accommodate in your work tape.
Sorry, just a question.
Yeah.
We don't need to check if they are primes, right? We can just go modulo all numbers from 1 to n squared.
Actually, that also we could do. Oh, sorry. Yes, absolutely. Yeah, I don't know why. Yes, of course that will do. Yeah. Okay. So by the way, so this this thing of iterated matrix product, for those of you who know what this is, this actually shows something stronger. In fact, this shows that this class called GAPL, this is a subset of CL. So you should technically think of GAPL as the computation of, the canonical task being computing the determinant. Okay. So, but anyway, I'm not going too much into this thing. I mean, I'm actually cheating here because on the left-hand side, it's a number, the right-hand side, it's a decision problem, but you know what I mean by these things. Okay. Okay. So now going further, we have gone from formulas. From formulas, we went to branching programs. Basically, branching programs is iterated matrix products. That's what branching programs technically are. From that, I want to go to circuits. Okay. So again, the setup that we are going to be working with is the circuits we care about are circuits of size S, and I'm thinking of depth D, which is typically assumed to be like something like order log S. Okay. And again, those who have seen algebraic complexity, I mean, this is like almost without loss generality. Oh, by the way, I am assuming that the plus gates could have arbitrary fan-in, but I'm assuming that the multiplication gates have fan-in too. This is a specific subclass of circuits, which are called SAC1, etc. But don't worry too much about those. This is a rough model. I mean, think of it as they are relatively shallow circuits where the pluses could be quite large, but multiplications are only fan-in too. So this will, I mean, it's a very natural subclass of circuits to deal with. Okay. Now I want to basically show that if F is computable by a small circuit of this type, I want to once again say that there is a transparent computation of F possible using not too many registers, not too large a program, etc., etc. Okay, now let's try to ask, why doesn't the old Buhrman and Cleve trick work? If it is an addition, addition gate in Buhrman and Cleve was like you literally just do the programs one after another, right? You just keep translating stuff. Multiplication was the only thing that was maybe a little trickier. So why can't I do the same thing where I start off with the top gate? If it's an addition gate, then I do each of the computations separately and concatenate those programs. And if it's a multiplication gate, I will again do each of them separately and do that weird commutator-ish thing. Okay. The problem is something that is true for formulas, which is just blatantly false for typical circuits, is that if you take your top gate and look at the left part and the right part, the sum of their sizes is the size of the original formula. And if things were usually nicely balanced and stuff, that you can basically say that both of them are roughly half the size, and then you get a decent recursion. But for circuits, it could just be the case that if I ask you, like the top, let's say the top gate was a multiplication gate, and I look at the left child and the right child, and I ask, what is the size of the circuit for the left child and the size of the circuit for the right child? For all I know, it could be both S-1 or S-2 or something. Because, I mean, circuits are allowed to reuse a lot of the computation inside. I mean, the difference between a circuit and a tree is that in a formula, the out degree was just 1. So, you know, I mean, once you show up here, you can't show up elsewhere. But in a circuit, you could have these gates that sort of feed into like different parts of the circuit. And so the standard going top down and breaking it up, etc., the size bounds don't match up. Okay. So we need a different method to do this. And what we are going to do is to try to do this one layer at a time. Okay, so let's say there's a bunch of gates in this layer. I will assume that, I mean, it's not hard. We'll assume with a lossless generality that the circuit is layered. It looks like a plus gate maybe, and then a bunch of product gates, and then a bunch of plus gates, etc. And things only feed in like from layer I, it only goes to layer I plus 1. Okay, and we're going to try and build programs this way. But now we need to do something a little different. We can't sort of say, take a program that computes F, take a program that computes G, and I will tell you how to compute FG or F plus G or something. What I should now instead do is take a program that computes all the polynomials you want in that layer. Now build a program that computes all the polynomials you want in the next. So that's how we should be building programs. At the base, everything is a leaf. So everything is an input. So they all have, there is a program of, if it has L leaves, there is a program of L leaves such that, you know, each of those registers, like for example, each gate is associated with some register, and they all got translated or something. And we need to somehow do this some sort of band by band in some sense. Okay. So what I'm going to do is like, we're going to set up some terminology. Like each gate will be given its own bag of registers. There'll be a bunch of very few registers, maybe 3 or 4 or something. But every gate will have its own bunch of bag of registers. Okay, so each gate G has a few registers. Let me just call this RG, 0. I don't know, RG, I don't know, maybe there are 6 of them.
So earlier, even in the Benner-Free thing, the computation was doing something a little stronger than what branching programs are, right? It does this R1 goes to R1 minus R2.
Yeah. So that's what actually.
It seems like it's allowing you to take 2 things.
So it's not quite branching programs, but what I'm saying is like these sort of things that you can compute using iterated matrix products. Those are things that are expressible as branching programs.
No, I want to say right now, when we're trying to do circuits, we're trying to emulate circuits now. That, I mean.
Oh, shouldn't this extra power help you? Is that your?
Yeah, I mean, what's like, I'm trying to understand what's non-trivial about this step. Like, why can't we just do some sort of gate by gate?
It's just that then the size will probably add up a lot more than you want to, right? Because you will basically say, like, if okay, let's for the moment pretend that there were gates, I don't know, H1 through HS, which are getting its value from G1 through GS. Maybe H1 is a product of some 2 things, G1 is a product of some 2 other things, etc., etc. I mean, maybe like, you know, there's some connection, weird connection that's happening this way. Now, if you just ask yourself, how much, if I want to first compute H1, how much are you going to end up taking? Maybe you end up taking a certain size based on what was the program you had for G1 and G2. And now for H2 will be something else, for H3 it will be something else, etc. I don't know if adding up the sizes for each of the gates is going to be something that's going to give you polynomial size overall. Okay, so I want to be a little more judicious in how this size shows up. So the setup we are going to have is that every gate is going to have its own private set of registers. Let's say RG0 to RG5. And whenever we are talking about a program that computes the gate value, I will assume that RG0 is going to get translated by the corresponding value. So the G0, the zeroth whatever register in its bag, that's the one that's going to get translated when we do some transparent computation. Okay, so we're going to assume that we have some program such that for all the gates in maybe this layer, so let's call this program PL. We are in layer L for now. All the gates in this layer, the corresponding zeroth register got translated by the value that those gates had. That's what you have managed to achieve so far. I want you to build this PL plus 1, where things that were in the next layer, I want to somehow get or whatever, translate all of them by a certain. This is what we are trying to do. Okay, but we will do this sort of gate by gate, but then we'll put them together in some slightly nicer form. Okay, so let's focus on one gate in layer, the L plus 1th layer, and ask ourselves, how does that gate relate to the previous layers? And depending on what that thing is, you might have to run maybe 2 different kinds of programs. So the first easy case is if whatever, this layer actually looks like, it's a sum layer. Okay. So in this case, the program that I'm going to build is I'm going to replace R at 0 with R at 0 minus, let's say, RG1 0 minus RG2 0 all the way till how many did I have? RGK 0. I mean, I'm just writing shorthand. This is actually possibly K different instructions. I'm just writing it as one giant instruction. Okay. And now I run the program PL. Okay. And then I'm going to run R at 0 is replaced with R at 0 plus RG1 0. Okay. And in fact, not even going to undo the program PL at this point. If you want, you can undo it, because the point is the registers I care about at the next level, where the H car registers, those have gotten the right values. So I can proceed with the one gate above in some sense. But if you really care about it, you can make sure that other registers return to the old value. So hopefully this is clear that this is going to compute. The H is going to get the RH0 register is going to get translated by summation GI. Because you first untranslate by the original values of the registers. Now each of these registers got translated by the corresponding GI. Now you translate again everything. And I hope I don't need to do this calculation. So again, plus is not complicated. Maybe let's just write down. So the number of H registers. In this case, it's actually just one. We didn't even need other H registers for auxiliary stuff. Okay. And what's the size of the program? So it's basically going to be the size of PL plus, I don't know, it could be potentially as large as 2s.
What was PL?
PL was the program that computes, that translates these registers by the values of the GIs. So everything in layer L, you manage to compute those values. So that's what PL is doing.
In layer L, you have a bunch of gates. For each gate, you had 5 registers. And what PL does is, in the 0th register for each gate, it adds the
corresponding computation. And now we have managed to show that at H I have managed to add the computation on the 0th register. In this case, you don't need RH1, RH2, etc. For the product, we will need some extra auxiliary stuff.
I mean, this silly thing, like you said, we don't need to do PL inverse. Because we don't.
So because once you have the values of RH0 to the values at the H registers translated, all subsequent computation will be working from layer L plus 1 to layer L plus 2.
What it meant is, we don't need to do PL inverse here. We can do it.
Yeah, they can do it once right at the end. It won't matter. Anyway, the next one is going to, the next one will incur it will double. The size will double, you'll see.
I mean, we still do want to eventually get every register to what it
Right.
That
At
will
the-
be a PL
Okay,
inverse.
well, actually, maybe I should write the PL inverse. Let's not complicate things here. Let me do the PL inverse here. It's not going to hurt at all. Okay, so the length, what is the length going to be? The length is going to be twice the length of PL plus something that looks like order S.
So you are just trying to say on some size. That's all.
Yeah. Okay, and the number of registers we are using is 1 for each. Okay, there's no each, there's only one edge that we are working with. So for the gate H, we only needed one register. We didn't need some extra auxiliary stuff at all. Okay, of course the trick.
I have a question.
Yeah.
So if the L+1th layer has some, let's say, T many gates, then we will do RH0 till RHT here, or like what?
Okay, yeah, so I'll just come to this. Right now I'm doing it at one gate at a time, but we'll eventually have to put all of them together.
Yeah, because I mean we can run PL once and then like use it for all of them.
Right.
Yeah.
We'll run PL once, but the setup, etc., you might have to do it per gate. Like for example, by setup, I mean is these moves. I might have to do that for each gate, but PL is going to run once. That's it.
Yeah. Okay.
So you could do RH10, RH20, blah, blah.
Exactly.
PL.
That's what is going to happen eventually. Okay. Now let's do product. And this is something I can't remember. So thank God for Notability to be able to put these spoiler things. And this is some magic bunch of moves. So in this case, let me just write down all of them. Okay, so it's a bunch of instructions that look like this. Okay, so this is what this is basically my program PL. I'm assuming that G1 and G2 are the two gates that you care about.
So these R0, R1, they are H registers.
So R0, R3, R4 will be the H registers. R1 will basically be RG0. R2 will be whatever, RG10. R2 will be RG20. So R1 and R2 actually belong to those Gs. I'm just going to use them for this computation. But R0, R3, and R4 are those that are for H. R0 is where it's eventually going to show up. R3, R4, unfortunately, I just need them in the intermediate computation. Okay, it's some complicated program. So we are just going to track what is going to happen. Okay, so let's do that on the side. So there is, tau 0, not tau 1. Tau 0, tau 1, tau 2, tau 3, tau 4. So to begin with, tau 0 becomes tau 0 plus tau 1, tau 2 plus tau 1, tau 4 plus tau 3, tau 2. That is the first instruction. This instruction results in this. Now you run the program PL, which in particular will mean that this gets incremented by G1 and this gets incremented by G2. That's what the program PL does, right? Everything in the G layer, something will change. And these are the only two registers from the G layer we care about, so it will change. And now I'm going to replace R3 with R3 plus R1. So this is going to become this plus tau 1 plus G1, this plus tau 2 plus G2. That's what happens in instruction, whatever these instructions are. Okay, and now this calculation. So I have to add R0 plus R1, R2, whatever is the current value of R1, R2. So that's going to become what? There is a tau 1, tau 2, plus there is a tau 1, G2, plus there is a tau 2, G1, plus there is a G1, G2. That's what happens. And right now we have come here. Okay.
Here we are not trying to be careful about computation.
Actually, it will turn out to be even not, but I don't know if I can use it for something, but yeah. And now notice, this is the program which is just PL in reverse. Your untranslating thing, I just wrote it in the other order. Okay. So that effectively becomes, this is what happens after you run PL inverse. And now I need to replace this with R1, R4. I mean, I need to subtract R1, R4 and R3, R2 from this thing. And what is the R1, R4 is going to be what? Minus tau 1, tau 4, minus tau 1, tau 2, minus tau 1, G2, and then R2, R3, R2 or whatever, minus tau 3, tau 2, minus tau 1, tau 2, minus G1, tau 2. And I just hope everything cancels off. So there are two tau 1, tau 2s, and there are two negative tau 1, tau 2s. So fortunately, those go. And tau 3, tau 2, tau 3, tau 2 goes. Tau 1, tau 4, tau 1, tau 4 goes. This and this.
So it doesn't work if it's not.
Oh,
One thing which is in wrong order.
oh, there's one which is in wrong order. Oh, okay, I didn't pay attention.
No. You can see it's tau 2 G1 and you have minus G1 tau.
Okay, I don't know if maybe I wrote it wrong or it, but okay, but I'll trust you. I mean, like, yeah.
You wrote it.
No, he didn't.
I
The
think
first
you
one he
wrote-
wrote incorrect.
Right.
Oh, the first one didn't write wrong.
The tau 2, because see, he's written G1 first, but he's written the tau 2 G1 second, which doesn't make sense, right? If it was in the first
Oh,
bracket.
okay.
They-
Okay, yeah. I mean, like, if you are more careful, you probably, I mean, maybe it works even if it doesn't commute, but yeah, I don't care. Okay. Great. So what's the length of this program at the end? So it's going to be what? It's twice the length of PL plus some chiller, like 1, 2, 3, 4, but actually it's like 1, 2, 3, 4, 5, 6, 7, 8. Plus 8, right? So that's what you have. And the number of registers you're using for H is actually 3 now. Maybe I wrote 6 there, but 3 is enough. Okay. So 2 of these registers belong to the corresponding G1 and G2s. But H has this extra R3, R4 that is using for some local computation.
So you need to reset the values of the R3, R4 also.
So we are not going to do, because the next time onwards, the only registers you will be using are the H0 wala registers. They have the corresponding values. If you want, you can reset it as well. I don't think it matters for the size. Okay.
No,
So
I mean, as it stands, you would need to run PL and PL inverse one more time. Not to reset.
sure. Instead of that 2, if it was a larger number, I don't think it would matter. Yeah. As long as it's a constant, it's fine. Okay. Now going back to what Varun was asking. Now this we were doing for one gate in that layer. But there are many gates in that layer. Okay. But if you look at what is happening in both these situations, the plus situation and the product situation, it looks like you need to do some setup moves, apply P, do some other setup moves, apply P inverse, and maybe do some finishing moves. Okay, this is what it looks like. So the way this is going to, the final program is going to be like, there is going to be the program PL, and there's going to be the program PL inverse. And now you run the setup moves for the setup 0 for all H's in that layer. One after another, you just put the corresponding, I mean, if you had like 8 instructions or whatever that was there, you put all of them. That, and maybe between PL and PL inverse, you once again have a bunch of setup moves. Maybe there's a different set of setup moves for all H. And then you have a bunch of setup, I mean, the final moves. Huh? Yeah, or tear downs or whatever. Yeah, I mean, like whatever, opening, middle game, and end game. Yeah. So that's what you end up doing. And it's important that PL is running once, and that works for all the gates in that layer. And then you're doing a bunch of setups, and then again PL inverse happens that undoes all the gates in that particular layer.
In the sense that the fact that this was a circuit.
Yes, yeah, that's being used here. Okay, so the total length is basically going to be twice the length of PL plus the sum of all the setup moves overall. So for each gate, the setup moves was some constant. Maybe it was like order S or something for the addition gates. But basically this will become this, let's say this plus poly S. Okay, I mean for addition, there was this long setup move that we had to do. Okay, so it was about S. In the multiplication gates, there's constantly many things, but one for each of the. Okay, great. So the final length, if you unravel this thing completely, will turn out to be something that looks like 2 power d times poly S. Okay, and the number of registers you are using is like order S because it's like 3 registers per gate. D was the depth of the circuit. Okay, and usually the right regime of parameters to work with is when D is like log S, like order log S. In which case, the number of the program length is actually going to be like poly in S. Okay, so this, I mean, for those of you who know, there is this larger class which is called log CFL, which is like the Boolean analog of VP. For those who know, this actually shows that it's not just that NL is in the catalytic log space class. Actually, this class called log CFL is sitting inside, because log CFL is captured by these sorts of circuits. Okay. Okay.
So the NL group we saw was that DVP is in.
Yes, it's like BBP can be put in catalytic log space in some sense. Okay. And in fact, the main theorem of oh, by the way, I didn't even mention who these people are. It's Buhrman, Cleve, Koucky, Loff, and Speelman. Okay. Yeah. No, this is Florian Speelman. Yeah. So, so in fact, there is this class called TC1. Again, we haven't done circuits in the complexity part yet. So maybe TC1 is something that will be alien to people. But for those who know, TC1 is a class that is like this, that we believe is even above log CFL. Okay, and in fact, if you look at their proof, they actually show that you can actually do this. Somehow the key extra thing you need to do is powering. And somehow they show that once you can do powering also in this world, you can do the whole thing. But that's a part I'm not very familiar with. So, but this in some, at the moment, as far as I know, this is the largest class that we know of, which is contained in catalytic log space. Okay, and it's just that mentally you should think of it as like well above L. Like NN itself, I would think of as like above, and then there's log CFL on top of it, and TC1 seems to be even above that. Okay, good. So now we have sort of at least hopefully seen that catalytic log space can do some funky things. I mean, like things that you don't expect to be doable with just a logarithmically large work tape. Somehow you're able to make use of this catalytic tape contents, even though you have no control on what their original values are, and that you are expected to put them back at the end of your computation. Okay, despite all of that, somehow you are able to make use of that extra space to do substantially more than what we could do in log space. So maybe one question to ask is, okay, fine, we are trying to see what can we do in catalytic log space. And now maybe you can now ask, wait, how large is catalytic log space? In the sense that, can it do all of P? Can it do all of NP? And like, how far does it go? So if I care about one stupid upper bound, okay, certainly catalytic log space is no more than P space. So in P space also, you have polynomially large work tape. Just that you are not expected to return it back to its original form. Okay, so certainly, I mean, like with this work tape, etc., you can, I mean, you can't do things that are beyond P space for sure, right? Like that you can't do. The question is, what's a good upper bound? And surprisingly, the best upper bound we seem to know is this class called ZPP. Again, we'll do ZPP in the next module, which is like randomized computation and stuff. These are zero-error probabilistic polynomial time algorithms. And surprisingly, catalytic log space is a part of ZPP. Again, this is a great problem set / exam question. Okay, I mean, it's not a hard thing to do, but the thing is, it's very surprising that, in the definition of catalytic log space, etc., there is no randomness. So it's somehow really surprising that you're able to give an upper bound of it using a randomized class. Okay, and secondly, when we do ZPP, we'll see, I actually don't know of many interesting problems in ZPP. In fact, there's only one problem I know in ZPP, which is not known to be in P. Okay, so surprisingly, it's a very weird upper bound. Okay. Oh, this thing of finding a square root modulo of prime. I mean, a decision version of that. That's in fact the only problem I know of that seems to have a ZPP algorithm, which is not known to have a polynomial time algorithm. And somehow this sort of says that this weird catalytic log space class is sitting inside ZPP. So it's certainly within some second level of the polynomial hierarchy or something, but we actually don't know if, do we have a better upper bound, or is this the best upper bound that we have? So that's still open.
It would be very natural to try to upper bounds here. By some log square or anything.
Okay, actually, I don't TC1, is it in log squared space? I think it is. Right?
No, that's not upper bound. No?
Oh, sorry. No, sorry. Yes. No, I was just trying to see what we know of. Does it already contradict this thing? Okay. Yeah, well, it would be, is catalytic log space within deterministic log squared space? I don't know if we have disproved that, or is that still open? For all we know, it would be. Okay. So for those of you who, there's been some reason.
How do we know in log space? In the past, log space to the power, log to the power 1 plus epsilon. I mean, we can't apply the space hierarchy here, right? To say that.
Yes. As far as I know, yeah. We don't know if we can put it in. Can I put an upper bound of D space polylog n for some this thing? We don't know that yet.
No, that is true. But we also do know that whether catalytic log space contains some log space to the power 1 plus epsilon.
Oh no, in fact, the best, whatever, from the bottom, the best that we know is TC1. Okay, and on the other side, the best that we know is ZPP.
So you explain that catalytic log space strictly contains log space.
Yeah.
And that should be unconditionally proven.
Yeah, hopefully, yeah. It should be doable. Yeah, but yeah.
That's analyzed.
Yes. Okay. It's great, actually. I'm very happy with how the time worked out. So basically, this is all I wanted to say for today. And I'll just tell you what the agenda for the next two things is. So next time, we will do this thing called the tree evaluation problem. We will go over what the question is and Cook and Mertz's thing. And you will see a lot of catalytic computation that's somehow sitting inside. I mean, in fact, the way I think Cook and Mertz write it, or maybe Goldreich writes it in his exposition, is that it's how to use bad programming practices to get good space efficient algorithm. It's like complete disregard for memory safety and everything. So we will see that there'll be a recursion that will be happening. There are some local variables that are there for one level above in the recursion, and this guy will go and modify those variables. I mean, but we basically will say that, look, I will use your local variables, but when I finish doing, I will put it back to what it used to be. So when I give back control to you, you will be able to whatever local variable you have. So that's going to be the rough idea of how this.
In the beginning, if you have a code down, it's your problem.
Yeah. Yeah. So, okay. So we will do the tree evaluation problem. That's going to be the agenda for next Wednesday. And then once we've seen tree evaluation problem, we will see Ryan-Williams's, or rather a slightly weaker version of Ryan-Williams's here. Okay, so are there any questions?
So, Bernard and Cleve show that with tree branching programs are all of formal.
Right.
And in fact, for constant width, we know that this is equivalent.
This is equivalent, right.
So what happens for super constant? So, I mean, if I want to compute determinant, what's the smallest size of matrices? So that the size of the The number of matrices is per one.
Yeah, right. So the Mahajan Vinay branching program for the determinant, that is n squared sized matrices.
But
I mean n squared cross n squared. That's the thing.
but smaller.
Yeah, actually,
So the moment the size starts growing,
uh-huh.
at some point it will the obvious divide and conquer algorithm for getting a formula for that matrix product will stop failing and they will stop working.
Right. Uh-huh.
And then
yeah,
I mean that maybe that stops working almost immediately because the moment it becomes super constant,
yes,
the fan outs become super constant and they can't.
Yeah. So basically, what you're asking is if I want to look at iterated matrix multiplication where the width is super constant, is there some perhaps a very, very slow growing function such that you can somehow say that this is still computable by small formulas or something of that, right?
Yeah, or it captures it.
Or it captures it or the other. Okay.
Is there a dichotomy?
Okay, good point.
How does the transition happen?
So I just know that Benor and Cleve, for instance, I mean, there is this version where you can Benor and Cleve gives you any formula can be written as a program of size s squared instructions using 3 registers. Yeah, you can make it s to the 1 plus epsilon by using more registers. But I don't know of the sort of thing that you are asking for. But yeah. Anyway, okay, so that's all. Is there any other questions? Okay, cool. So then we'll meet next Wednesday, same time, 2 to 3:30 p.m. For the tree evaluation. Sorry?